So here we are at the end of the semester, and I want to highlight some of the things that we missed, I guess we could say, over this semester. Things that we didn't spend a lot of time on, and I think it's time for me to answer for those crimes. So here are the things that, in my view, we did not touch on very much. We did not do a deep dive into trigonometric identities, and there is much more work we can go much more work you can do in solving trigonometric equations. So here's my first comment on these two things. A lot of times when we get into trig identities, and even some of the stranger trig equations that we didn't solve, is that doing these things are really, it's really designed to reinforce your algebra skills. So to me, we don't do all these trig identities where we make the left side look like the right side to improve it's less about improving our trigonometry skills and more about improving our algebra skills. I have the same thoughts about solving trigonometric equations. So in my mind, the deep dives into these two things, trig identities and solving trig equations, kind of comes down to reinforcing our algebra skills. So to me, this means we missed out an opportunity to reinforce our algebra skills. In favor of more trigonometry style ideas. Part of the algebra skills that we're missing is not just the manipulation, but the ability to read expressions. So that's one of the places that coming out of my class, you might be a little bit weaker. Coming out of my class in this particular instance, didn't do trig identities, skipped a little bit of the trig equations business. So we missed an opportunity to reinforce our algebra skills. This is not just manipulation. This is also reading expressions, not just manipulations. But reading skills, the more important reading skills. So this is what I think we miss out on by kind of giving these things a lighter treatment. Due to time constraints, due to interface constraints, all kinds of things. That really just come down to excuses, I suppose. The important thing to remember about trig identities is that if you get stuck on a problem, there's probably an identity that can simplify things. So that's my first rule for trig identities. If you get stuck, start looking at trig identities that might be related. So how will missing out on thousands of trig identities how missing out on thousands of trig identity proofs, typically the kind of problem that you run into to practice your trig identities and your algebra skills, your manipulation, how missing out on these trig identity proofs affect us in the future. These are the things that you need to watch out for as a student who missed out on these thousands of trig identity proofs. The aforementioned missed opportunity to reinforce algebra skills. So there's going to be less algebra skill training. And also, it's not going to be your first instinct. So you miss out on an instinct for identifying when an identity might be useful. The way that we can overcome this so more important for us, maybe, what can we do about it? The important thing to remember is that if you get stuck and trig functions are involved, look for some trig identities, even if you just have to go look up the trig identities. For the most parts, we would have to spend a lot more time on trig identities if we want to build a student who in the future gets stuck on a problem, says, oh, I'll think of this identity, and I remember my half angle identities because I memorized them. So more important than actually having all these trig identities at your fingertips is knowing that these identities, there might be an identity that can help you. Know that there might be a trig identity that will get you unstuck. Know that there might be a solution to the problem out there that's locked up in trig identities that you probably wouldn't remember anyway, even if I covered them. Part of the evidence that I have for this is when I see people complain all the time about modern approaches to doing arithmetic and how it's based on place value and this emphasis that we tend to make on place value these days. And people that are my age, or plus or minus, 10 years my age, before education became as politicized as it is now, people complaining about students where our attempts to teach young people about place value. And the complaint always has the same form. Why don't you just do it the way that I did it? And my response is usually, okay, first of all, I don't think I want to use your first reaction to getting stuck on your kids' math problems is, first of all, you got stuck on your kids' math problems, so I don't know if I want to use you as a model for what should be done. And number two, we did try to teach you this. You just didn't remember it in favor of the algorithm because it was efficient. So quiet, you. I usually don't like to shut down debate like that, but there's no debate here. If you're on record as being bad at math, then I don't think I want to use you as a model for what should be done to young people in teaching them math. And second of all, we did try to teach you using place value. Full disclosure, apparently we failed at it, but that doesn't mean we should stop trying. Third of all, that dumbass algorithm that you're trying to press uses place value. Anyway, so more important than remembering all your trig identities now is in the future knowing that when you get stuck, there might be a trig identity for this. I should go looking for that. All right. So another thing, the other thing with trig equations, a lot of times with trig equations, we're just taking algebra equations that we've done before and sticking trig equations. We're just putting one more level in the equation. So usually when we're solving trig equations, we're just taking an algebra equation and inserting a trig function in it, just adding more steps. It's just algebra with more steps. So most of our weirdo trig equations So most of the extended look at trig equations involves inserting trig functions into equations that we're already familiar with. Let me give you an example of what I mean in this regard. So for example, in algebra, we might have an equation that looks like, let's say, x squared I just realized the example that I was going to do is not going to do what I want it to do. Let's suppose we have an example equation 2x squared minus x minus 1 equals 0. This nice classic quadratic equation from algebra, and it is even factorable. We would solve this by factoring. We'd say 2x minus 1 and an x minus 1 equals 0. 2x plus 1 is minus 2x plus 1. So we get the two solutions, x equals negative 1/2 and x equals 1. So we can turn this into a trig equation. One of the trig equations that is running around your trig book would look like this. 2 cosine squared x minus cosine x minus 1 equals 0. And our approach is unsurprisingly the same. But instead of a polynomial in x, it's the same polynomial, but x is now cosine x. So this has become a reading exercise and identifying the type of thing that we're dealing with. We want to see the quadratic in this trig equation. We want to see the quadratic in the trig equation so we can apply that same thinking. And to give you a false impression about how things work, this is in fact factorable in cosine x. So this is going to be 2 cosine x plus 1 times cosine x minus 1 equals 0. And once we have a pair of factors equaling 0, one or the other has to be 0. So we get cosine x is equal to negative 1/2, and cosine of x is equal to positive 1. Now we're just solving the simple trig equations that we did deal with in this class. So the cosine of 1/2 means we're dealing with a 60-degree angle, and cosine is negative in quadrants 2 and quadrants 3. So I want 60-degree reference angle in quadrant 2 and quadrant 3. So this part is going to make us think of a 60-degree reference angle in quadrants 2 and quadrant 3. So 120 and 240. And then the cosine of x equals 1 is going to be a quadrantal angle. So cosine of 0 is 1. So that's going to give us a 0-degree angle, or 360, and so on. So we're just trying to combine the equations that we might be familiar with trig functions, and we're just inserting the trig functions into older equations. I still think there's more percentage, at least in this early stage, of focusing on trying to solve equations by doing inverse operations in reverse order. So if we think back to the graphing things that the graphing work that we did, think about what happened to the x before the trig function, what happened to the x after the trig function. So after that, it's just a matter of kind of playing with these objects, and just kind of seeing what works. So let's see. I'm going to look at another simple example that kind of combines the two big things that we missed out on. So let's take a look at this equation. Let's suppose we're looking at cosine squared x equals 1. So if something squared is equal to 1, this means that thing is equal to plus or minus 1. So if I just square root both sides, I got to remember the plus or minus. Anything with an even exponent is going to produce two real solutions. So this means that we need to solve cosine x equals 1 and cosine x equals negative 1. Just like in the previous problem, if cosine x equals 1, then x must equal 0. And if cosine x is negative 1, so cosine is the x, so we go from 1 to 0 to negative 1 to 0 to 1. So going around the circle. So cosine of x is negative 1 when x is 180, or pi. I didn't write degree on the 0, so apparently I'm doing the problem in radians. And there are our two solutions. Cosine of 0 is 1. 1 squared is 1. Cosine of pi is negative 1. Negative 1 squared is 1. So we can check. Cosine of 0 is equal to 1. And 1 squared is equal to 1. For the second one, we would say that cosine of pi is negative 1, and negative 1 squared is 1. So they both check out. The second one here, negative 1 squared is positive 1. Because when we write cosine squared, we mean cosine of pi and then squared. So the notation, cosine squared pi, when we write cosine squared pi, this is the notation for cosine of pi and square the result. And so when we take the negative 1 and square it, we end up with positive 1. Oh no, I'm checking in the original equation. Yeah, if we took out the square, cosine of pi is -1, and that checks into this one, in this one here. But I went into the original equation. So one of the angles that one of the double angle identities that is useful for us is the cosine squared. Taking cosine squared and dropping it down to cosine of 2x. In some scenarios, not this particular scenario, in some scenarios, like when you're in your calculus class doing integration, Calc 2 specifically, this is trouble. This is easier. Having not a power of cosine, but the cosine of 2x is better for us. We don't have reasons why right now. But if I have the equation cosine squared x equals 1, I should be able to replace it with cosine squared with this identity, 1/2 plus 1/2 cosine of 2x. Now we notice that we have, now if we read this equation, we've got x gets multiplied by 2, then we take the cosine, then we multiply with the result by 1/2, and then we add 1/2 to it. That's the order of things that happened in this expression. So let's undo those things to the 1. So I'm going to subtract 1 from 1/2 from both sides. So 1/2 cosine of 2x is 1 minus 1/2, which is also 1/2. And then let's divide by 1/2 to get cosine of 2x is equal to 1. Now let's solve for, get rid of the cosine part. If the cosine of 2x is equal to 1, so just like up here, where x is 0 and x is equal to pi, cosine of 2x is equal to 1 means that 2x is equal to 0. Now at this point, we're thinking, what about the pi? Where does that come from? How are we going to get that? Remember that cosine, we don't just get 0. We get 0 and any multiple of 2 pi. So that's 0 plus 2 pi, because there are infinite number of ways to represent 0. And the pi over here is going to be pi plus 2 pi. We can always add a full circle. So now if I take the 2x equals to 0 plus 2 pi, times any number of, if I divide by 2 now, I get 0 plus pi times k. I get all the multiples of pi. So this is going to give us 0 and -1. So it's going to give us 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi and 6 pi and so on. Is this how we would solve this equation? Not really. But if we notice, what we want to do to get better at trig is to know all the things that we can do with trig. Right now, this is bad motivation for learning your trig identities. So right now, it's harder to motivate your trig identities. This is how it was done to me. You're going to need this in calculus. And to which my response was, and I thought this perfectly reasonable at the time, and I still do, it's like, oh, but I'm not in calculus. I'm in trigonometry. And when I got to calculus, and I did need to know my trig identities, I looked them up. Now, I'm not advocating that we should just replace school with, hey, just go look it up or Google it, man. Because one of the important things that we're trying to get is knowing what questions we can answer. Do you know what I mean? I think I've said it before in this class, but it bears repeating. You should not graduate from college with fewer questions than you started college with. When you graduate from college, you should have more questions than when you matriculated. When you're a teenager, you know everything. So you go to college to learn what you don't know and start asking questions. Never trust someone who says they have all the answers. Ever. Anytime someone tries to present a solution and they lead with, it's simple, when the problem is obviously complicated, then that person is just not earning their place at the table. You don't have a simple solution to a complicated problem. If there was a simple solution to the complicated problem that you think you've solved, it's just demonstrating that you completely misunderstand what the problem is. You don't even understand the question. Because don't you think someone would have done that before? How much ego do you have to look at a complicated situation and say the solution is simple, just do this? You don't think someone has thought of that before? That's a lot of ego right there. You know what I mean? So I guess all this is to say, there are some things that we missed out on. I think I made some judicious choices about what to emphasize and what to de-emphasize as we go through this trigonometry class. And in the future, you're going to find situations where you clearly disagree with me, and you'll be like, "Oh, Leach, you betrayed us. Why did you not cover more trig identities? I failed calculus because of you." And that's fine. Go on to ratemyprofessor.com and write me some bad reviews. Failed calculus because of this clown. Totally okay with that. You know what I mean? Anyway, today's our last day. You've got some quizzes up on the Canvas, so make sure you go and make some corrections to the Canvas quizzes. I'm going to be grading more trig quizzes today, so if you lose some points on those, go get those points back. Or maybe you still have like 98% even with those points missing, in which case you could say, you know what, I'm going to focus on other things. If that's the case, then focus on other things. I'm going to be really upset if I find that you're turning in assignments at 11:30 on the 28th, 11:30 p.m. on the 28th, because that means you left things to the last minutes, and I've been trying to convince you to not do that. But I'm equally going to be upset if you're turning in at 3 o'clock in the morning on Wednesday, because why are you staying up till 3 o'clock in the morning to do work? Aren't there more important things? This is just a trig class. You know what I mean? Anyway, I do want to thank today's the last day class. So that's it for today. That's it for this week. That's it for this semester. I want to say thanks for playing. I had fun. I always have fun doing trig class. Trig class is always one of is always a class that I get easily distracted by cool stuff like that complex number thing. The zeros are complex numbers. So thanks for going along with the crazy things that I wanted to do at random times. I hope you can forgive me for the things that I missed out on that you're going to need in the future. I hope that I prepared you well enough that when you find that you need something in the future, you know where to get it. It's Google. You know where to get it. Some of you are going to be in IT professionals, just remember that when you're an IT professional, that means you're better at Google than everybody else. Because like the computer says, this error code happened, and for the most part, you just Google that error code, and it'll tell you what's going on. So I hope I've prepared you enough. I hope you appreciate Trig a little bit more, and I wish you great success in your future math classes. Hopefully in a couple semesters, you'll end up in my Count 2 class, and I can really do some damage. So thanks for playing, everybody. Appreciate you all being here.
Thank you.
It's been fun. Have a good summer.